Swayam Prabha. Digital India. Educated India.
So in the previous session we had learned about the different tabs, right? We just got a brief introduction into the different tabs. So in this session we are going to learn how to do a simple modeling, and we are going to learn about some techniques which are known as bottoms up approach and few other simulations, right? So let's get started. So the first tab in the main menu, now we are going to focus our attention specifically on the main menu, is on the preferences. Okay, so let's go in order. So first of all, when you click the preferences, this is very important, you want to click on structural, because ANSYS has a lot of options like thermal, magnetic nodal, magnetic edge, electric simulation. So these are the things we are not interested in. We are only interested in structural simulations, and this checkbox will allow us to only focus on those options which are seen in different tabs, under different tabs, which are only focusing on structural, right? So we would always like to click this tab preferences and set this to structural before starting any simulation. So you just hit OK. The next tab here is preprocessor. Under preprocessor, the first thing which we want to do is the element type. Element type is what defines what is the type of that small discretized elements which your entire model is going to break down into, right? This is also something standard. So we click the add, edit, delete, we hit add, we go to solid, and we go to solid 186, 20 node 186. So why do we select this? This is a long history of things, like why do we select a certain material type. So I'll just give you a very brief, like materials, this element types have actually evolved over time into, from the discovery of ANSYS to how ANSYS has gotten improvised over the years, and many of these element types are specific to points, many are specific to the lines, and many are specific to volumes, right? So solid 186 with a 20 node means 20 places it can, or 20 vertices where this entire element can get deformed or shaped or adjust to any kind of curvature or any kind of thing in your model, any kind of shape in your model, and fit within that, right? Like this. So certain organ models can have extreme curvatures, some pointy edges. So a normal element, let's say circular element or spherical element or a cuboidal element may not fit there correctly, right? So 20 node allows for a lot of flexibility within the element to fit certain crevices and curvatures, right? So that is why this is known as 20 node 186. This is typically what we use for majority of the solid modeling, and it works just fine. Why not other models like 185 and others? We are going to skip that discussion, like let us just focus on the 20 node 186, right? You can read it up if you're interested to look at the element history, right? So after selecting this, you just hit OK and you close out of this, right? You just make sure this is written as type 1 solid 186. If this is not written, you may have cancelled out of the other tab and you may have not selected the element. So this is good. So we close out. The next thing which we do is we go out of this tab. So element is done. Real constant is something which we are not going to use for majority of the volume models. So let us skip that one as well. Third is known as the material properties. So click on this material properties, and I would just request your attention on just the focal points or the options which I'm focusing on here, because rest of the options you will not be using that much, right? So these are the key options which are of use. So under the material properties, we go to material models. Okay, when you click on material model, this is the tab which opens up. Under the material model number, which is set to I think 1, yeah, it is set to material model number 1. You go to, on the right side, structural, you go to linear, elastic, isotropic, right? When you hit this 4, it finally takes you to this tab where it is written as Ex and PRXY. So what are these two terms? Ex is known as the modulus of elasticity, the same as what we have learned so far in the experiments, the modulus of elasticity of the curve, stress strain plot. PRXY is Poisson's ratio. Okay. So let me place a modulus of elasticity dummy value of 10,000 and a Poisson's ratio of 0.4. Fairly flexible tissue, right? I cannot go beyond 0.5, even 0.5 and I cannot do, otherwise the solution will not run. That's a mathematical limit, right? Like I just cannot, it has nothing to do with answers, just Poisson's ratio has to be within certain ranges. So this is good, 10,000.4. If you want something higher, you can write it in different forms also, like 1E5 or 1E4 is the same as 10,000, right? So if I hit OK, just hit OK once, and if you hit, you see this linear isotropic, if you click here you will see 10,000. So this is another option of writing, that you just write 1E4 or 1E7 or things like that, right? What are the units? So like I've already told you, ANSYS is unitless, so we are going to assume certain units which are very much by the rule of thumb. So any modulus of elasticity, 10,000 here is megapascals. Okay, this is what I'm going to assume. That way I am going to get all my stresses in megapascals. All my dimensions are going to be in millimeters, right? This is my assumption, and based on that assumption I'm going to interpret the results accordingly. Okay, so let's do OK and let's exit out of this. My material models are now set. Now I exit out of this one as well. The next one which is of importance, sections is not very important for what I'm trying to do. Next one which is very important is the modeling. So under modeling, I'm going to run through a bunch of tabs as we go along. The first one and the most commonly used one is the create. Under create, you see several intuitive options like key points, lines, areas, volume, nodes, elements. Let us focus on the key points. Under the key points, there are so many options. Which one do you want to select? Let's select inactive CS. Please select only the ones which I am showing, that way you can focus on building everything from scratch, the soft tissue model, right? So key points on active CS. What is CS? Coordinate system. So what is your coordinate system? You can see your coordinate system here, X, Y and Z. So I can either place a number here like key point number 1 and write down the location of the coordinate locations of this point, or I can put a number 2 and write down the locations, or I can leave this vacant, let the computer automatically place numbers, right? So if this can be left vacant, why do I ever need it? Because there are cases where you, in a certain organ, there could be a section of the disease where you have certain key points of concern which you want to hold very tightly. You want to make sure that 102 key points to 345 key points are the key points where the disease is occurring. Maybe I need to change that model or modify that model at a later stage. That's why sometimes control over the key point numbers are important, but in this case I am not worried, right? So let me make something very simple. I want to make a put a 0 0 0 as my, this is the origin specifically. So this is my first point I am going to put in any analysis, not necessarily origin, you can start from somewhere else as well, but you need to have at least a starting point, right? Okay, so should I hit OK or should I hit apply? This is another important part. So if I hit OK, this tab is going to vanish. If I hit apply, this tab is going to come back and stay here, and I can keep on putting new numbers here, right? So let me hit OK first. OK, done. So you cannot see the point per se, like there is a way to see the point, I'll show you in a second, right? So this is gone. I'm going to click this again. Now if I set this point one more time and hit OK, then it is going to create another point in the position of origin. It can have 1000 points in the origin place which is of the same value, but that will really confuse us in selecting the right point. So you want to have only one point at one location, right? So the next point which I want to make is along the x a point of 5. So 5 0 0, z nothing. So I'm just moving towards the x. So rather than OK, if I do apply, it has created a point, right? I'm not able to see it somehow. Let me hit fit view. Now I can see this point, right? This active CS is not gone. Actually, this is hidden on the back side. So I'm just going to click it one more time. So this is the point which I've created, point 2. Now I want to go towards the y direction, maybe 2 points, right? Apply again. This is point 3. Now maybe I want to go back to where I started almost. So I'm going to go 0, right? Apply, right? So 1 2 3 and 4 points. Now should I, to exit out of this, click this cross button or OK or cancel? So what I would advise you to do is always hit the cancel or the cross button. Do not hit the OK, because OK will again create another point in place of 4, right? So let's say I hit OK by mistake. What happened? You have another point which is superimposed on 4. So you have 2 points there. So now how do I get rid of this point, right? So first of all, I want to make sure that this 5 points are there. In order to do that, I go to list. I go to list key points coordinates only. So this clearly lists the 5 key points with their unique coordinates, with a lot of decimal points, because there are some points which can go in huge decimals, right? So I can clearly see I have points 4 and 5 with the same coordinate system or the coordinate numbers, right? So these are kind of redundant. I have 5 points, so this is verified. Now what I want to do is, rather than I want to delete this 0.5 first before I go ahead with my model. So I scroll a little down and I go to this delete option. Under this delete option, I again have the same kind set of things which I had under create. Under delete, I have the key points. I'm going to hit this key point, right? When I hit this key point, I want to click at this location. When I click this location, the computer automatically gives me 2 options, whether I am trying to select key point 4 or I am trying to select key point 5. So in this case, I am trying to select key point 5, so I am going to hit OK with that. It has selected key point 5, and if I hit OK one more time, key point 5 is gone. How do we make sure? By listing it again, listing key points coordinates only. Now only 4 points are there. This is how you create a point and you can delete a point. Okay, so I can exit out of this. Now I don't want to delete anything further. I go back to create. So under create, now I have 4 points. I want to now create a few lines, but I want to create a few more points so that I can make a cuboid or something like that, right? So let me create a few more points. So I want to create maybe. So in place of this, I had this 0 0 0 as the first point. So rather than 0 0 0, I want to go to negative z. So negative z of -2. Z is pointing outside the screen, so I want to go inside the screen, right? If I do apply, it creates the 0.5. So the previous 0.5 is gone, so this is the new 0.5. Then I want to go with up till the x of 5. Apply, right? Then I want to go 2 points here, kind of parallel, and then I want to go 0 points here, right? I can either hit apply and cancel out or hit OK. Both of them will work fine, right? Now if I click on the screen, the points are still remaining. I want to make sure of one thing, which you will encounter in the upcoming as we do more and more simulations, that we have to look at a certain screen which is showing either key points or lines or areas or volumes. everything can be looked upon only together using looking at multiplots. I'll explain what that is. So let's say these are the points. The next thing which I want to do is create lines. So let me get out of this key points. Next is I want to create lines. I go to lines, lines. I want to create straight lines. So how do I create straight lines? This tab is open. I just want to click on the 2 points and it will create a straight line. Okay. So I can start from anywhere. I can start from here also. I want to create a line like this. It will automatically give me the option unless I click on the point, right? So I'm going to click here. Then I'm going to click here again. I'm going to click at the 7, here, 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 then here, 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 here. These are the different lines which I'm drawing, right? So now I have created a set of lines which is forming a cuboid. Okay, and I just hit OK. So now when I click on the screen, the lines are gone. Why is that so? Because I am looking at, just see the thing, the pointer on the screen, it is known as points. You're looking at points. You're in the point screen, that's why it is just showing you points. So if you plot key points, it is going to show you key points. Now why are the numbers gone? Because we have not switched on an option, which you find out in plot controls. You go to plot controls, numbering. This is a value. This allows you to switch the key point numbering on and click OK. Now the key point numbers are back. Now if I want to plot lines, I go to plot lines and the key point numbers are still there. Okay. So can I plot areas? No. I have so far only created points and lines, right? Can I delete certain lines if I have created them by mistake? Yes. Let me create a line by mistake and I want to delete this, right? This is a line, let's say I have created by mistake. Okay, I want to delete this line, right? Go to delete operation, lines. Okay, here I have 2 options for the lines, right? I went somewhere wrong. So under the lines, you have 2 options. You have very similar options for the areas, volumes, and other entities. For the lines, you have an option of deleting the line only and deleting the line and below. So how are these options different? When you delete the line only, it still retains the points which are associated with the lines, right? There could be extra points which are associated with the line which is not associated with any other line, right? So line and below deletes not only the line but the associated points. Lines only deletes the lines, not the associated points. That's the idea. Here you will not see a huge difference because the endpoints are associated with several other lines. So if you do just lines only, it will work. Even lines and below is fine, right? I'll explain you what this is in much more depth as we go along. So this is how we can delete a line. Now we have a set of lines which we are happy with. The next thing is we want to go to create and make areas, right? Under areas, go to arbitrary and go to by lines. Okay. Here it is shown that you need a minimum of 2 lines to create an area, and you can select a maximum of 12 lines in this case because you have 12 lines only in your entire model. If you had 500 lines like in certain organs, you can use so many lines, right, to create areas. How can you create an area with 2 lines? That's interesting, right? Like you need at least 3 lines to make a triangle. So when ANSYS is talking about lines, it is talking about any line, be it a curved line or a straight line. Okay, so I can have 2 curved lines make an area, right? Their curved lines are typically known as splines, right? So that's why the minimum count is 2, the maximum is 12. But here we know very clearly that what we need is 4 lines to create an area in this model. So let us do that. So I'm going to click this top 4 lines. Let me click somewhere by mistake and see if the area is developed. So this is saying, giving me an error message that key point 2 is referenced by only 1 line, improperly connected line set for area from lines command, right? So it's not like you can do whatever you like. So the computer will throw you some error messages if things are not proper, right? So I'm just going to close out of this and go back to here. Now I'm going to select the lines properly. what if I've selected something by mistake? So I am here in the pick tab. I can go for unpick, and then the cursor just kind of rotates downward. In pick it is upward, and in unpick it is downward. This can also be done by using the right click of my mouse. I can just right click and toggle from pick to unpick, right? So with the unpick I select this and hit OK, right? There is nothing OK because I'm basically trying to create an area, right? So I want to pick the right one. Let's say I've picked something by mistake. I go for unpick and pick again, and then pick the right one, and now I go for area. Done. So the first area is created. Next I want to create the other 5 areas, because I'm looking at 6 areas which are going to encompass the entire cuboidal volume, right? Fairly intuitive. So let's go for the next area. 1, 2, 3, 4. You can also do apply. That will allow you to keep this tab open, right? So that's the difference between OK and apply across places. So keep an order in which you're creating the areas, because after a point you may see visual illusion and you may not understand which area you have not created. So it's good to keep an order and proper discipline while doing the like different modeling. So 1, 2, 3, 4, apply. 1, 2, 3, 4, apply. So now I've created 4 different areas, but it is already creating a visual illusion. So let me cancel out of this and just make sure. So now I cannot see any of these areas because I'm in the lines tab. So if you want to switch to areas tab, you will be able to see the areas now nicely. So you clearly know which ones are the areas like which you have not created, right? So we go back to this option, we select this, this, this and this, and hit OK or apply. The back part is created. Now the last area which is remaining is this and this. Yeah. Now that you have all the areas, now you can create a volume out of this. For a completely closed body with all the areas well defined, you can create a volume. Even if you had one area missing, you will not be able to create a volume. The computer will throw you an error. So let's create a volume. So the next thing is we are going to the, I'm going out of this areas tab, I'm going to the volumes tab. Again under arbitrary by areas. So I have an option of minimum 2 areas and maximum 6 areas. Can you create a volume with 2 areas? Yes, you can create a volume with 2 curved areas, right? And maximum 6 areas are available, right? So if I select, let's say 1, 2, 3 and want to create this volume, it will give me a discontinuous area set for volume command, right? I want to select all the areas to create the volume. So this is just good to know that these kind of error messages will come through. So I'm going to select 1, 2, 3, 4, 5, 6, or I have the option of pick all. That is another option. Anything which you're looking at the screen can be picked up. This may not work when you have a lot of surfaces and a lot of different organs or models where you have to pick something specifically to create a volume. But in this case, it's interchangeably used. It can be used either ways, right? So let me just reset. Reset lets me unselect everything. So if I just do pick all, it has done the job of hitting pick all and doing the OK as well. Now I have a volume. To verify whether I have a volume, let us volume and area. Let's click on list areas. I can drag this a little bit better to see a better visualization. So I have 6 areas covered by these 1, 2, 3, 4, 5. These are the lines, and like 4 lines forming each area, and then basically this is just a loop. So lines are this, 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 and you have a no elements, no nodes, nothing, but these are the 6 areas. If you know look at plot list volumes, then you basically look at the volume which is there. Yeah, this is just one volume. So this shows one volume which is covered by all the 1 to 6 areas, right? So I exit out of this. This was a quick verification. Now I have a volume. Now what is next? Now let me get out of the modeling tab. Okay, my model is ready. So that was the step 1 of finite element modeling. process. I need to have a model by any means, right? Be it through scanning, be it through CAD software, importing from CAD software, or I built it. But the building methodology, like which I'm using currently, is known as an approach which is known as bottoms up approach. This is a point to be noted. So what is a bottoms up approach? Bottoms up approach is when you start from the very bottom of the hierarchy with the points. You go from points to lines to areas to volumes, not the other way around. That is known as a bottoms up approach. Why would I not get the volume directly? Why do all this exercise of going from points to volume? Good question, right? So the answer to that is many a times, like in majority of the times, actually, when you're looking at a complex organ systems or a complex model, you will not be able to create it using regular functions which are available in ANSYS or any kind of CAD software. Normal functions are create a cuboid, create a cylinder, create a sphere. But if you want to create a oval kind of a curvature, create a kind of semi-rectangular and some curvature kind of thing, which are complex systems, you have to work with points, lines, areas and volumes. You cannot be working with direct to volume kind of simulation. Yes, you can in certain aspects where you have scanned models. Scanned models are already in the volume form. You can use them directly. But here I would like to mention one caveat. Do not think that just quickly scanning or doing an MRI scan or some form of hand scanning is going to save you a lot of time, because those models are extremely crude. They have a lot of surfaces, jagged surfaces sitting one on top of each other with a lot of gaps. So they need a lot of post processing. You need to send them to through softwares to make sure it is a closed volume. There are no small little micro gaps and things like that, right? But when you do the bottoms up approach, you're very clear on what you're doing. These are the points, these are the lines, these are the areas, these are the volumes, right? Right. That's why bottoms up approach is a very important aspect to be learned as a part of the ANSYS system, right? Okay. So this modeling part is done. The next part which I want to do is meshing. Okay. Okay. One thing to note is meshing can only be done if you have selected the element type and you have selected a material property. If you have not selected either one of these, it will not allow you to use the meshing. Okay. So this is good to know. You click on mesh tool, right? Mesh tool has a bunch of options which I am going to explain as we go through the different sessions. But let us for now click the mesh option. It is automatically set to tetrahedral kind of mesh elements. Let us just hit the mesh option and click this model and just click OK. So this is now discretized the entire model into small elements. These are all volume elements. So if I want to list what are the elements, list elements, nodes and attributes. How many elements have been created? 193 elements have been created, small elements, by breaking down this entire volume. Think about how complex this would get when you have a really big and sophisticated kind of complex figure, right? And also the material type assigned as material 1, and these are the nodes. Why is it not how much should it be? Like these are 1 2 3 4 5 6 7 8 16 and 17 18 19 20 20 node solid 186. So you're looking at 20 nodes per element, right? Close out of that. So the meshing is done. Now the next part is we want to assign loads and boundary conditions. So just skip all these ones in between, checking controls, numbering controls, archive model, coupling, these things you can skip. Let's go straight to the loads. Under the loads you have define loads, and under define loads you have apply. This is where you need to go, right? So what kind of loads we are trying to apply? Structural loads. Okay, from a loading standpoint, I had explained in a finite element model, the minimum criteria which is important is at least you need to have one fixed surface or some fixed lines. You cannot just have one fixed points or nothing fixed, right? There needs to be something fixed. So in this case I am going to apply a fixed boundary condition of displacement on areas, right. I am going to select this area, hit OK, and this allows me to select along which direction the area is to be constrained for movement. So I am selecting all degrees of freedom, all DOF, right, because if any degree of freedom is open, the computer will not give you the solution. Something needs to be properly fixed or hinged. Okay, so I'm going to fix this and hit OK. Okay, so this model is fixed here. The next thing which I want to do is I want to apply a pull force here. So let me apply. I can apply a force here, or I can apply pressure. So if I want a force to be applied, force has to be, it's a vector quantity, it has to be applied at a certain point. So which is the point? I don't know. So let me apply a pressure, which is force distributed over an area. So I want to apply a pressure on the area this, right. What is a positive pressure? What is a negative pressure? Positive is something which pushes the model, negative is something which pulls the model. Okay, so I'm going to apply a pressure of negative 0.5. Okay, okay, loading done, right. The next thing is I want to go for solution. Everything else is gone. I can just close down this loads option. I want to go for solution. So now I am done with everything. I have selected element type, material properties, I have created the model. Based on selection of the element and element type and the material property, I have been able to create the finite element model or the meshed model. I have also applied the loads and constraints. Okay, is the load and constraint only to be applied after meshing? Not necessarily. You can apply this load and constraint beforehand also, before meshing also. But one thing to be noticed, where are you trying to apply the loads and constraints? This is the point of concern. So there are two things which we are going to take, and the terminology we are going to use it like this. One is the geometrical model and one is the mesh. Okay, mesh will only happen after you have meshed the geometrical model. Geometrical model has key points, lines, areas and volumes. The mesh has elements and nodes. These are the two different classifications. Okay, so whether I want to apply my loads and boundary conditions to the geometrical model elements such as the line, point, area, or as a volume and total I cannot be applying, so it's either a point, line and area, or I want to apply the load to the meshing elements like on a mesh node or a mesh element surface. So that is the choice to be made. If the choice is the first one, you want to apply loads and constraints to the geometrical model, then you do not need to do the meshing before you apply the loads, right. You need to do meshing anyways to run the solution, otherwise nothing is going to work, right. So if your model doesn't have a mesh, the solution will not run. What I am specifying here is when do you want to do the loads and boundary conditions application, right. You can either do it if you are applying loads and boundary conditions to the geometrical model before the meshing, or if you want to apply the loads and boundary conditions to the mesh elements or the nodes, mesh nodes, then you can only do it once the meshing has been done. Hopefully this point is very clear, right. So after clarification of this point, we would like to go straight to the solution. In solution, you should always check this box, analysis type and new analysis, and this is by default set to static. Just hit OK. What is this we are doing? This is just like a clear screen kind of option, but this is a clear screen for the results. So you want to make sure while you're working with different models in the same file, it could be sometimes that the computer is storing some previous results data. Earlier you had applied a force of 5 newtons, the same place now you are applying a force of 2 newtons. So if the computer saves the previous data, it's going to apply 5 plus 2, 7 newtons. This may give you wrong results, right. So this analysis, new analysis type basically clears all the results from the database. It makes sure that whatever simulation you're running is brand new, right. So with the solution new analysis done, I next go to solve current LS, current load system. Okay, this will give you some comments like this. If you hit OK, takes a few seconds and it says solution is done. I close this, I close this, I see something here, but I still cannot see the results here. So in order to see the results, I need to go down and go to something which is known as general post processing, right? Under general post processing, I need to plot results. So under plot results, I want to look at the deformed shape. Do I want to look at the deformed shape only, or do I want to look at the undeformed shape in the original form and the deformed shape together, or do I want to see the deformed shape along with the undeformed edge, not the undeformed entire model, right? So these are the three things which you can look at. So deformed shape, you cannot really tell what may have deformed. So if you click on this again, deformed and undeformed, this shows you the entire model, what has changed. And if I look at deformed edge, undeformed, deformed shape and undeformed edge, this is how it looks like. It shows just an outline of what the original model was and where my model has become, right? So let's assume this is a piece of soft tissue. This is what I wanted to explain. Let's assume this is a piece of soft tissue which is subjected to a tensile loading, which in this particular case very similar to what we would do with a UTM, right? So let us look at a quick animation on how this model is going to move as we apply this load and this deformation is occurring. So you go to plot controls, you go to animate, and you go to deformed shape. You will have the same options here, and I can select something like this, deformed and undeformed edge, and just let it be. So this is the animation, right? You're slowly seeing the edge kind of deforming. The tensile loads are being applied. But one thing to note is this is a quasi-static or a static simulation. So this is actually not the real transition which is going on. It's more of a initial and final result, and it is showing like a transition visually, right? It's visually appealing. If you want to show this to somebody how this model is behaving, this is how you show this. You can change the delay here, and that will make the animation much more faster. If I change the delay completely, it's going to make the animation completely very fast, and I can slow down the delay. I'll have to stop this and come back to original and then close this down if I want to close this animation. So very cool thing to work with, where we can analyze so many exciting models, right? The next thing which we want to look at is known as the deformed results. This is just the deformed shape. And one thing to note is, please do not go by the visual appearance. It could be that you have selected a model which is built up of steel. Can a steel deform this much by 20 millimeters? It cannot. So this is a visual appearance. This is not visually you are not looking at a true scale, right? So there is something which is which you can see under plot controls, which is known as style, and you go to something which is known as displacement scaling. If you click this, you will see you are looking at a scale of 1020, right? 1000 times your results have been scaled up to showcase what you're seeing. If you're looking at true scale and hitting OK, you don't see anything. Let's run an animation here, right? Animate, deform shape. You do not see anything going on, even if I change the delay. Does it mean what we are seeing visually is wrong? No, not really. It's just a scaled up version to show you something nice visually, but the results are going to stay the same. Only the visual appearance is going to change. So I'm going to set it back to the default automatic visual appearance so that things are showing, you are seeing something exciting, otherwise you're just looking at nothing. And why are you looking at nothing here in the true scale? Because the material property I've set it to that high, 10,000, with such small amount of pressure, it is not causing any kind of very little displacement, right? Like micro displacements which are not visual to the naked eye. That's why you are seeing. If I increase the pressure to 10-15 times more, you will see some good amount of displacement. So let me set this back to auto calculated and hit OK, right? You see this deformed shape again. The next thing which I am going to look at is the deformed results, or the final solution results. So one thing which doesn't work very fine in the student version of ANSYS is the contour plot and the vector plot. These are supposed to work fine in regular ANSYS, but this is just one caveat. I've noticed this while teaching quite a few classes, that the student version has some bug due to which this contour plot doesn't work. But there is another option where you can look at. You go to something which is known as result viewer down here. You click here. So this is another viewing option. So here what you can look at is a bunch of results. So you can, under this, choose the result item. You can select the DOF solution, which is degrees of freedom solution. You can look at the displacement vector sum. Once you have selected this, this is in form of a contour. You can hit the plot results. So this is how your entire model is displacing. Very interesting to look at, right? So this is color bar is basically showing you the extent of the displacements. So you're looking at 0 to a very small displacement, and all these displacements can be assumed to be in the order of millimeters, because that's the assumed unit set which I've assumed for my entire simulation, right? And we are going to consider that further as well, like millimeters and megapascals. The 0 to 0.245 e raised to negative 3, so that is basically 0.245 times 10 raised to power negative 3 millimeters. That is the maximum displacement which you're seeing. That's why it's not visible to the naked eye. Where is this maximum displacement occurring? Let's pay a little bit of attention into the screen. So you see this mx at the very top close to the red. So that is where the maximum displacement is occurring. You see another point which is mn, where the minimum displacement is occurring. Whenever you see blue, that means almost the result is close to 0. Not always blue means 0. In some cases there could be some other values of blue, but in this case it is 0 because this surface is completely constrained or fixed. Nothing is moving there, right? And in the red part, it is undergoing the maximum amount of displacement due to being the free end, right? Few things to notice. Let us take a look into the solution pointer. So the text on the very top left, you're looking at nodal solution. You're not looking at an element solution. You're looking at the solutions smoothened over the different nodes. You're looking at step 1, sub 1, time 1. These are not of much importance. You're looking at a DMX. DMX is the maximum displacement, right? Displacement max. That is what the DMX means. That is given by 0.245 e raised to power negative 3, same as the color bar. Then the next one is SMX. SMX is known as the solution maximum. Here the solution you're looking at is displacement only, so it's the same value. Let us next look at the stress. So under the stress, we are going to primarily study von Mises stress. Why von Mises stress? Why not principal stress, or why not plastic stress? Look up von Mises stress if you are very interested in understanding the stress. This is a very common type of stress which is used across research and industry to compare results with experiments and in different computational models. It gives us a very nice flexible single value of stress which can also handle very large deformation. So this is kind of an equation, stress equation, which gives a very right and accurate value for complex simulations involving a lot of contact pairs, non-linearities, like complex shapes and things like that. So von Mises is a rule of thumb, just like solid 186. We go for always von Mises. So von Mises stress contour plot. Let us hit plot results. This is your stress distribution. Okay. So you have quite a bit of stress which are localized close to the area of constraint or fixed area, which is intuitive, and you have low stresses on the other end, right? And in the between you have almost 0 stresses. So here, point to be noted, blue is not starting from 0. Blue is starting from a minimum value of 0.17608, right, in megapascals. Everything you are reading here in the values are in megapascals based on our assumption, right? Where are the max and min? Minimum is here in the blue region, and max is located across the red regions, this specific red region where you're looking at mx, right? This is the coordinate system. You're looking at the x, y, and z. Let's take a look at the text on the top left. You are looking at a DMX, which is the displacement max, which is still the same, 0.245 e raised to negative 3. However, the solution max, solution here is in the form of stress, not the displacement. So solution max and solution min, SMN is the solution minimum, is 0.17608, same as the color bar. SMX is 0.526803, same as the color bar, right? And this is the distribution. This is of concern because whenever you have a area of very high stress with zones of very low stress around it, it can create fracture, but that is not the case here. You see a fairly uniform distribution. The red is transitioning into yellow and then to green and so forth, right? And also the value of stresses are super low. It's not going to create any damaging effect. Another point to be noted here is while we are studying stress, we can keep on applying any amounts of loads and that will keep on deforming the object or model to any extent. But do we have any fracture criteria here in the ANSYS system? We do not. Okay, this is a point to be noted. You can just keep on applying pulling force, keep on applying pulling displacement, the material will keep on pulling. It will never see the fracture point. That is the difference between an experiment and a computation. Computation just takes a value, moves the system according to the mathematical calculation. So unless and until we define a fracture criteria that when the stress goes beyond, let's say 27 megapascal or 35 megapascal, please declare fracture or stop the test. ANSYS cannot detect it. Okay. So in general, ANSYS or any finite element software doesn't have any fracture criteria. We need to explicitly define that criteria. Or sometimes what we can do is we do not define that criteria. We keep on running under different loads. We run simulations and finally figure out. We look at the max stress value. Let's say the ultimate tensile stress value at which this particular tissue specimen or specimen is going to break is, let's say, 15 megapascals. That's the ultimate tensile stress value. I'm just giving an example. So right now it's much lower than that. Let's say I apply higher pressure and it keeps on, these colors are going to stay the same, but the numbers are going to keep on changing, right? So let's say this goes to 16. That means I have gone over the limit of ultimate tensile stress. Now my system will fracture. So I want to keep the simulations and keep everything below the 15. I can go beyond, but if I go below, I will be able to analyze that this is where I am not violating the maximum stress limit. This is very important. So theoretically, I can have an understanding that let the stresses not go beyond this point. If it does, I have to reduce the overall load to run another simulation, because if it goes beyond the ultimate tensile stress values, it is going to fracture or rupture somewhere, right? This is another point to be noted. I have applied a linear mechanical property with a modulus of elasticity and Poisson's ratio, which is not typically the case with soft tissues, as I've explained repeatedly in several classes. So what I would like to mention here is stress upon strain is given as the modulus of elasticity. That's the calculation. So whatever you are seeing in stress values, you will see a very similar representation. So my modulus of elasticity was 10,000. So you will basically see the strains in terms of a 10,000 multiplier and very similar distribution. So let us look at the von Mises strain. It can be basically scaled or predicted. So von Mises total mechanical strain I'm going to look at. Let's focus on the last value, 0.5268. Let's hit this number. So what has happened now? Almost close to 0.5268 only. 0.530 e raised to power negative 4. That is basically divided by 10,000. The structure of the color pattern here is almost similar. The solution max and minimum is based on the color bars. They have changed slightly, but the stress and strain profiles are almost similar, right? You can further look at different other aspects such as shear stress, elastic stress, total mechanical and thermal strain, things like that you can look at. So let us take a very quick look at XY shear total mechanical strain. How does it look like? So when you look at shear strain, you are looking at a very high strain at a certain point. but the values are still very low and almost lower values in the other zones. If I change this to YZ, I see little bit of difference, right? So all these different forms of stresses and strains can be looked upon. I close out of the result viewer now. What I want to do is I want to animate a stress result using this, right? So go to animate, instead of deformed shape, go to deformed results, go to stress and go to von Mises stress. Okay. If I hit OK, just take a look. This is how the stresses are getting generated. Very nice and peaceful diagram to watch, like, which can clearly showcase how the stresses are getting propagated, how they are going to evolve, right? Which are the high zones, right? So this is very important for majority of the simulations or majority of the soft tissue tests, which we cannot find out through experiments. These kind of very internal stress development can only be studied through computation. If I increase the speed, this will show you very quickly. टाइम है 51 मिनट, ठीक है, और 1-2 मिनट करके बस कंप्लीट. Okay, so this is the animation which we are looking at. So let us stop this, we close it. Some more animations you can look at is let's say plot controls, animate, deformed results. You can look at DOF solution. This is nice to look at. Vector sum. So just look at how the displacements are propagating, how this entire model is getting stretched, just like in the UTM how the sample is getting stretched, right? Can increase the speed. This is how the stresses are distributed, right? I cannot change anything with the mouse while this is running, so I can only do that once I've closed out of this, right? I can move this and then run the animation again. Yeah, now you can clearly see it in different views. If I want a particular view, like an isometric view, I want to see it like this. I want to look at an oblique view, side view, top view, back view, very similar to a CAD software. These kind of things can be looked upon, right? Isometric view, I want to rotate this along the x direction by a certain angle, right? So these are some of the rotations. You can bring them back along the y direction. So these are just good to know, the direction, right? You can specifically choose how much to rotate also. There are some additional options, but typically you would not require those, right? Okay, so having said that, what all things have we learned so far? So we have learned all the tabs. We have learned how to complete one complete simulation by creating the points, key points, lines, areas and volumes using a bottoms up approach. We have learned how to select the element type, the material properties, do the meshing, apply the loads and boundary conditions. The absolute requirement is there needs to be at least one fixed constraint. The other loads you can have or not have the loads, but without a load it will not give you any solution of any value, but the solution will run, right? Then if you apply a load and finally run the solution, you have to go to post processing. Every time you have to do a new analysis before you run the solution to refresh all the previous results, and then you run the solution and get to the general post processing where you can look at the deformed shape, undeformed edge, different versions of the deformed shape. We have looked at displacement scaling, which is kind of a visual scale, how the computer throws the results to show you something worthwhile, but in true scale it may the story may be very, very different. But the scaling has nothing to do with the values which are shown here, like in the color bar or in the text. The values are going to remain the same irrespective of this visual scale which you do, right? So the scale is just for a visual appearance. Just when you want to showcase a certain simulation to your manager, or let's say to your PI or somebody else, right? And finally we have learned how to do animations with these kind of models and study von Mises stress, von Mises strain, and with a linear mechanical property they will have very similar correlation, but if you are going to change the different kinds of materials to non-linear, the stresses and strains would be very different. Also, we looked at the total displacement sum, and this will give us a holistic view of internal stresses, strains, as well as internal displacements, which we cannot see in the experiments. So this is the first key lesson of ANSYS, where we have done one simulation considering a soft tissue but with linear properties. We are going to slowly take baby steps in the upcoming session, where we are going to learn and pick it up from this model. Before I complete this, I would like to just save this model, to save as maybe Swayam model 1, right? So this is my model title. I have retained the .db, I have saved it. Now I am going to pick it up and resume from here only. So I am going to resume from this Swayam model 1 in my next session, and I am going to talk about what happens if you change the loads, if you change the constraints, if I change the meshing. Can you do that very quickly, or do you have to change certain things in the model? So stay tuned, and we are going to learn more about ANSYS and learn more about soft tissue mechanics here, and also take one or two examples where we have very complex models like the human foot, which I was just showing, placed along with the insole, right? So stay tuned, and I'll see you guys again in a short while. Thank you.